Okay, welcome to the next lecture in the arithmetic harmonic analysis. This week we'll be talking about the approximation formula for the discrete spherical averages. So we're finally getting towards a culmination of the course, at least in terms of proving the Magyar Stein Wainger theorem. Just to remind everyone briefly about our setup, we're looking at the integer points on a sphere, right? So we have this quadratic form. And we just look at the level sets. So for each lambda that's a natural number, we can define these points, which are subsets of the integer lattice. And we've already shown in the first part of the lectures that we have asymptotics as lambda goes to infinity. And we have also stated, but not proven, that there are always points as soon as you have 4 more dimensions. But we're always going to stick to the case where we have 5 or more dimensions, where we have some asymptotics for this, which is that. Oh, hello. The number of such points grows like, up to some constants I won't pay too much attention to right now, lambda to the d over 2 minus 1. And we use these to define our spherical averages by just taking the probability measure supported on that set. So we normalize it by the number of points, and we take our average to be just convolution with that measure. These are probability measures, so it makes sense to define a maximal function, which is just taking the biggest average at every point x. Great. And the Magyar Stein Wainger theorem was that this is a bounded operator, this maximal function. It's a bounded operator on LPZD to itself when you have 5 or more dimensions, and this Lebesgue exponent p is greater than the dimension over dimension minus 2. Right? This range is sharp in terms of p and in terms of the Lebesgue exponent p and the dimension d. We saw a couple lectures ago that if d was less than or equal to 4, this operator is not bounded. It's unbounded on any finite p, any finite LPZD space. And we also show that it's unbounded when d is greater or equal to 5, as soon as p is less than or equal to d over d minus 2. Right. And so our main approach is to use Fourier analysis, which means the circle method for us. And for that, we have a bunch of notations that I'll just sort of briefly recall. I'll leave up on the screen for a moment. We have our usual character defined over several rings. And then we have the continuous Fourier transform, the discrete Fourier transform, which goes from ZD to the torus, and then the inverse Fourier transform for that, which goes from the torus back to ZD. And the main point of this lecture will be to understand the Fourier transform of that surface measure that I just mentioned. So that, as an exponential sum, is just you sample wherever your sums, you sample all the points on your sphere, and you appropriately modulate them for each point C on the torus. Oops. And of course, you normalize by the number of such points. But we're going to work through, for most of today, with the unnormalized surface measure. And so that's just going to be this exponential sum right here. When C is equal to 0, this gives you the number of points on the sphere of radius root lambda centered at the origin, which is what we spent the first several lectures doing. And our proof for the approximation formula, which I'll state in a moment, is going to use that method very heavily. It's going to parallel it quite closely. So just a little bit more notation, right? We have these Gauss sums, which are averages that depend on the form, on our sums of squares. And they're linear, they're twisted linearly depending on your factor b here. And then we also have some smooth bump function that's going to localize us to a small neighborhood of the origin. All right. So what's the approximation formula? Well, this unnormalized surface measure, which is just the indicator function of the integer points on a sphere of radius root lambda centered at the origin, has Fourier transform. This is for every point C in TD, the d-dimensional torus, it has the following approximation. It looks like this sort of mammoth right here in the middle, plus some error term, which I'm calling E of lambda, or actually Fourier transform for that. And this E of lambda gives you a convolution operator, which is an error term. It's the remainder from this approximation that I'll start explaining soon. It satisfies a nice dyadic maximal function inequality. So for each window, big lambda to twice big lambda, we form the dyadic maximal function, where we take the supremum over all the little lambda inside that window of our error terms. And this turns out to be bounded by this exponent right here. But sorry, by this factor right here. So it's lambda to the d over 4 plus epsilon. So ignoring the epsilon, which is a little bit, well, you can remove it. Magyar Stein Wainger proved it without it, but we won't need that today or in this course. When you appropriately normalize this, you're going to normalize by a lambda to the d over 2 minus 1 to pull that out, and the normalized error terms are going to be summable over lambda as a geometric, taking the big lambda as a geometric sequence, such as 2 to the j. And this will be as soon as d is greater than or equal to 5. All right, we'll see that in due course. I should describe, I'll come back to describing the main term in a minute. This part in green is what I'm going to call the main terms. I'll come back to them in a minute. Just to remind you what we did last week, we proved this transference lemma, which allowed us to leverage knowledge about operators on the Euclidean space to operators on the integral lattice inside of that Euclidean space. And it was in a sufficient generality so that we have these Banach spaces, finite dimensional Banach spaces, B1 and B2, which for us were playing the role of L infinity of n, where this, I've been using this notation to be just the integers from 1 to n, inclusive of 1 and n, right? So in particular, when you look at, so each of these, each f hat of c is actually a vector f1, fn, right? So f is actually a vector of this shape, and n we're thinking of as being arbitrarily large, but not infinite. It's finite dimensional, which, but in the limit, we can take n to infinity, so it's an infinite sequence. And that's the Banach space norm that we use is this L infinity one, so that at a point x, f of x in L infinity of n is actually just the supremum over all j in that range, the absolute value of fj, of x. Okay, so that's how we see the maximal function comes into play. Comes into play right here. The j and s. So for us, that'll actually be, say, we'll have some function lambda j, which is which taking this sup will give us the maximal function we need. Right. So we went over that in detail in the last lecture, and we're going to use it almost at every step of the proofs today, at least in terms of the approximation formula, where we want to bound the error terms. We're using it, we're going to using it repeatedly there. It's hard to recenter this. Great. So let me remind you of that main L2 inequality that we're going to use in conjunction with the transference lemma. So this is going to be how we bound the error terms. So what we had some exponential sum that depended on two parameters, on c, which is going to be a point in TD that we've been looking at, and we have it being integrated against some modular factor, e to the minus 2 pi lambda theta, and we average over theta. If these are defining your multipliers on the Fourier side, then the convolution operator, there should be no not there. The L2 bound is just bounded by this expression right here at the bottom. And we saw this a couple weeks ago. We saw how to prove this, and we used it to prove Magyar's, well, a special case of Magyar's theorem on the discrete spherical maximal functions. Right, so this is going to be how we control dyadic pieces, this main L2 inequality, and the transference lemma. All right, it'll generally be a two-stage process. There'll be another trick that comes into play that we'll see in a bit when we need it. So before going back to the approximation, I'll just leave up here for a moment the various notations that I've been using, and I'll keep using without much comment on. Right. So how do we get to that approximation formula? Oh wait, do I state the approximation? Oh, sorry, I did not state the approximation formula again, like I thought I did. So let's go into what this is a little bit. So this approximation formula has a bunch of pieces to it. It has an infinite number of summands in various respects. So first we have the modulus Q. That's going to be coming out of the moduli in the circle method, right? And it's actually, you should be thinking about this as fractions. This double sum here in the first place is actually a sum over fractions A over Q, where these are reduced fractions between 0 and 1, right? So A is coprime to Q. And then, okay, this is just a factor right here, either 2 pi I lambda A over Q. But the main point now is this expression right here. This is a 1 over Q periodic, 1 over Q periodic function. Well, not quite. It's a 1 periodic function. And if I didn't have these Gauss sums right here, then this would be a 1 over Q periodic function, because psi, I've assumed, has supports, I think I said -1/4 to 1/4 in all directions. So when you do psi of Q C minus M, which actually happens to be psi of Q and then C minus M over Q, just by multiplication, right, by distribution, you see that this is actually supported right here in a 1 over 4Q to a 1 over 4Q box centered at the point M over Q. All right. But there is these Gauss sums that are actually doing something different as M varies. So the picture I typically have in mind here is I've got my torus. And for each one of these A over Qs, the important thing for me for a moment is just Q. I chop this up into boxes of length 1 over Q. This is TD. Say Q is equal to 3 here. So this is of length 1 over Q, as are each of these boxes in each direction. And this right here localizes me to some small box in the center of it. So there's no interaction between these boxes, right? And on each one of those boxes, I have this term acting on every single one of them. But these other term right here, these Gauss sums, are going to weight them differently. Okay, depending on Q and depending on the point M over Q. Great. And of course, I have this for every A and every Q. So I actually have about Q layers of this from this sum. And those get modulated differently by that character right there. And then, of course, I have an infinite number of layers stacked on top of that, coming from all the different moduli. Now, one thing that may alarm people is that there is this infinite sum right here, sum over all lattice points. That just makes this sum periodic. For each C in RD, due to periodicity, each c inside the fundamental domain from -1/2 to 1/2 in every coordinate, this localizing factor just picks out that box closest to c. Right, so if I have a c over here, then it picks out this m over q that's closest to it and puts it in that box. Great. Were there any questions on this at the moment? We're going to digest this a bit more, and we're going to see how it's useful later on. But is there maybe anything that I haven't explained that I should explain? This right here.
So Kevin, could you say a few words about?
Sorry, what, Rob?
Could you say a few words about like the decay of the Fourier transform of d lambda square root of, or sorry, d sigma square root of lambda, just to make sure that it's fast enough for the sum to converge?
Sorry, so for this sum to converge? Or this whole sum to converge?
No, for the sum in M.
So for the sum in M, my point here is that sum actually for every c only contains a unique point M. And all the other ones are non-zero.
Oh yeah, I see.
Yeah, so that's my point here. So the real question would be how is there enough cancellation or decay so that this sum, well actually that sum, is fine when you add them all up. And that we'll get to. Yeah, but thank you. Yeah, that's gonna take us some work to prove that there's enough cancellation on these. Great. Okay, so let's start to run the circle method. It's one of our favorite tools. Delightful, inspired method due to Ramanujan, Hardy, and Littlewood. So we go back to our time-trusted oscillatory integral, right? That we write the delta function on z or on zd later as this integral, right? This on oscillatory integral. And we've seen how to do that in the first part, and we've used that in the second part of this series as well, right? The first part being, of course, proving the Hardy-Littlewood circle method bounds for sums of squares. The second part being proving Stein's spherical maximal theorem, and this third part being the Magyar Stein Wainger discrete spherical maximal function, which I need to remember to call the arithmetic spherical maximal function. Right. Okay, so we use the same delta method as before, and I'll be maybe a little more terse on the details than I was in the first part, but I'll try and make this section also relatively self-contained. So we use this delta function condition by testing when we have a point on the sphere, right? So I want to know S lambda, of course, just to remind you, was all the integers such that this was true, and Q of M I've just written is the sums of squares in d dimensions. Okay, so integrating from 0 to 1 here, or as I've done over the torus, any window of length 1, we'll pick out when this condition right here is 0, which is equivalent to, of course, just Q of M being equal to lambda. But we had that this was equal to a sum over M in ZD, then Q of M equal to lambda of E of M dot C, right? And that's what this summand inside that exponential is doing. It's remembering the fact that we need this for the Fourier transform. Okay. And what we've done here is we've thrown in some smoothing factor that, like we did in the circle in our first treatment of the circle method. This was our function that was a tensor product. So in each coordinate there was some phi naught that was and the function phi was supported in the interval from -1 to 1. Sorry, it was 1 on the interval from -1 to 1 and supported in -2 to 2. So it looked a little bit like that. Should be flat here. And in every direction. And this factor right here, dividing by r, just expands that from, instead of -1 to 1, -r to r. okay? And R needs to be sufficiently large so you actually pick up all those lattice points, which just means that R has to be at least the square root of lambda. We're thinking about R as roughly the radius of something, hence why it's R. And when we're going to take a supremum over lambda in some dyadic window, which is also inconveniently called big lambda, we need to take R big enough so that it works for all of those averages simultaneously. Okay, since this worked for all R sufficiently large, by just taking things a little bit more sufficiently large, we're going to be fine. The unfortunate thing, though, is if you were to take a supremum over all possible little lambda, that's a natural number, there's no R that is big enough to do this, right? That you can't work with this smooth sum, and you'd have to work with the unsmooth sum, but the unsmooth infinite sum, which is actually very, very difficult to work with. But this saves us a lot of technical trouble by doing that right in here. Great. Yeah. So we've done, oh yeah, I've mentioned right here what that function was. Now I'll rewrite that integrand itself as some exponential sum. Okay, like we did previously. And that exponential sum splits into a product of d one-dimensional exponential sums, as indicated on here. We had this exact same formula before when C was equal to 0, right? So that this disappears, and this disappears, and that's just 0, right? And we use that to count the number of points on a sphere of radius root lambda centered at the origin. So now we're doing that by remembering all this linear information, C. I call that linear information because this right here, this C is interproducted with some vector n. That's the linear map, right? Whilst T, which is another parameter coming up in the circle method, is actually modulated by something, or sorry, is multiplied by something that's quadratic, the sum of ni squared. Okay. So that's the quadratic information. T is capturing the quadratic information, and C here is linear information. Great. So inserting that, this is just notation, right? Inserting that into our integral above, we get the identity at the bottom. So now that I've done that, the structure of our proof is actually going to be very close to the structure it was before. So we're going to use Poisson summation around each rational point A over Q. That's going to pop out of looking at that integral localized to intervals around A over Q. This Poisson summation means it has a dual lattice of frequencies depending on N over Q. And the 0th frequency will dominate the rest. We'll get to what we mean by the 0th frequency here. It's not quite the right thing, but it's still the thing closest to 0. Okay. As before, the bounds that we use and prove, since we're only using an arbitrary smooth function and not a Gaussian that has the best localization in frequency space and regular space, or sorry, in phase space, we are going to have to end up splitting into major arcs and minor arcs. The minor arcs, we use the Weil's inequality once again. That'll give us almost square root cancellation on there. And the major arcs, we're going to have to do some other approximations. Okay, that's so on the major arcs, we're actually going to use that Poisson summation bound and the 0th frequency dominating the rest. So the rest are going to be the first part of our error term. The minor arcs will be the second part of our error term. Then we process the major arcs a bit more. And so like before, we're going to complete the oscillatory integral into a singular integral using stationary phase. That'll be our second approximation for the major arcs and third error term. Then we extend the singular series. That'll give us a fourth error term. And so our error terms will be a compilation of all those 4 error terms, and we're going to have to control them simultaneously, which we'll do as we go along the way. Okay. And the worst bound amongst those 4 error terms will give us the worst bound, or the bound that I claim for the whole error term. Now the point of departure right here is in 7 and 8. So actually 7 it's not really a point of departure. It's just a more mature perspective. That singular integral we saw before was the volume of the sphere with a particular measure on it. Now we get the Fourier transform of that spherical measure. Remember that when C is equal to 0, so I'm saying that we get this spherical measure, that's going to be for square root of lambda, before we had the mass of that. And that happens to be exactly what happens when C is equal to 0. But we're caring about this more generally now. And it's going to be when we have C not necessarily 0. And the final thing is we will not actually be able to turn this singular series into a singular product. I have no idea how to do that. I'm not aware of anyone who does, and it's not necessary for proving Magyar Stein Wainger's theorem. Okay, so we don't do that last step. Yeah. And along the way, as we take control of these error terms, we're making repeated use of the main L2 inequality and the transference lemma. So, any questions at this stage about the overall structure? Hopefully, everyone has taken a moment to sort of remind themselves a little bit about what happened several weeks ago when we were doing this. At the very least, everything I'm about to do will appear quite familiar. All right, no questions then. Let's proceed with the fairy dissection from the circle method. I pick some level X, which will be large right now, larger than my radius root lambda. And we consider all of these rational points between 0 and 1. Okay. And around those rational points, we attach an interval inside of 0, 1, or actually inside the torus. And you could do so in a way so that these intervals decompose the torus, they partition the torus so that they don't overlap, or except at possible endpoints. And they all have length that depends on the modulus. Okay, so my level is X, and my modulus is Q for a fraction A over Q, which is, again, it's reduced. That's what this co-prime condition means. Then the interval I of A over Q is length roughly 1 over QX. And I didn't prove this, but I referred to Hardy and Wright's text for these details. Great, so let's use that partition to decompose the oscillatory integral we have, right? This, just like before, it turns this integral over the torus into the sum of integrals over the different arcs. Each one of these IA over Q's is an interval, which we also call arcs, due to remembering that the terminology, the original delta method that was used for the circle method was with the residue theorem, which meant you did actually have an honest circle in the complex plane. Right. And then these intervals corresponded to arcs thereon. Okay, so we shift the intervals so they're sort of symmetric about the origin, and that means we introduce these more symmetric intervals. And in doing so, that shifts our function h. Okay, but you apply a change of variables and you get to pull out this character, and this is the first part of the approximation formula that we see. Okay, and now that we have this expression, we're going to use Poisson summation on h of r to start getting a grasp of it. Okay. I'm not going to go through the Poisson summation computation. I am going to just state it here as a proposition. It's only a slight generalization of what we used and did before. Okay. I defined previously h of r. So again, remember hr of 0, we saw all of this. We didn't have these characters right here appearing. And now they do, and modulation turns to translation when you take the Fourier transform and use Poisson summation. So that is why we see this shift of C coming up over here. All right, these G's are the Gauss sums, which I'll recall their definition right now. Like they're normalized, they're d-dimensional. So for each of these fractions a over q, I have this as my exponential sum modulo q. And we also saw previously that these satisfied a nice bound, which I call the Gauss bound, for every q uniformly, and then depending on the dimension, they satisfy this bound. That should be a minus d over 2. Sorry, it actually is. There you go, 2 over q. Let me make that red just as a correction. Okay, just write it like this: 2 over q, so d over 2. Because I normalized by q the minus d. All right, this is uniformly for all m that are integers or integer points. Okay, so when we plug in our expression for h of r, we just have this integral here at the bottom right. Great. Nothing fancy so far, very close to what we've done previously. And previously we noticed that this function hr of t, x is Schwartz in x, right? And so we expected to have good decay, and we use that to say that we have the following approximation when c was equal to 0. Okay. Now we're going to just recall the bound that we used to prove that, because we're going to use it again now for c non-zero. So what is that bound? Well, so first off, I did state the bound with c non-zero in the first part of the course, which I'm referring to as notes 1 here. And the bound that we had was just you apply integration by parts, which I also call the principle of stationary phase, or it's also known as that, commonly known as that. And what we see is that we get this arbitrary polynomial decay as c goes to infinity at the cost of this term right here. So some growth depending on r and t, which we know t is relatively small. So that's going to be advantageous for us. Okay. So I'm not going into the proof of that. Again, we did this before. This exact expression, it wasn't just for c equals 0. It was for all c, and it was just integration by parts. So if you hadn't seen that lecture, you can do this yourself just based on that information. But it does allow us to get to our first approximation. So before I said the 0th frequency dominates, that 0th frequency is the one that's played by this function psi. I think I had a little psi before, and now it's a big psi. I mean the same function. Apologies for the change in notation. So just to remind you, of course, because it is very important, psi of qc minus n is, of course, psi of q, I think c minus n over q. So this is supported in a box that has side length roughly 1 over q and is centered at n over q. So that is where I've said in this, the sum always has one term, this sum right here for B1. Okay, this is a function defined on the torus. It's going to be our Fourier multiplier. And that gives the first approximation. And everything else is this remainder, this difference d. Now this is an infinite sum. I'm summing over all the lattice points that are not close to c. Right? So my dual lattice is the frequencies n over q. And I pick out the n over q that's closest to c. I throw it in B. And I throw everything else into D, into the difference. And this 0th frequency is what I mean. That is the n over q closest to c. That'll be the main term. Everything else is going to be an error term. Right? So at this stage, oops, I should have the ZD Fourier transform of this indicator function. It can be written exactly as this expression down here at the bottom. Okay, and this part will be our first main term. This latter part will be our first error term. So let's get on to seeing why that's an error term. So to do so, let's define some convolution operators. These are defined by Fourier multiplication, like we've seen before. All I do is that the operator big B of 1aq lambda applied to a function f from zd, to say the complex numbers, is done by, if I look at the Fourier transform of that operator applied to the function, it's just multiplication by b times the Fourier transform of f. And then so to get back b of f, I just apply the inverse Fourier transform. Same thing for d. So my averages now for each lambda, right? I can write as this finite linear combination of operators right here. And I get to write it as such because that incorporated the whole torus, right? That delta function, that delta method. And now just using the fact that number of points on a sphere of radius root lambda centered at the origin is basically n to the d over 2 minus 1. We know these averages are bounded by this factor times the sum of convolution operators. Great. Okay, so how do I handle this difference? Well, that's going to be in this first lemma. So our first error term is this one. Remember, I want to handle, I have this error term, e of lambda, and I'm looking to control the sup over lambda between a big lambda and twice big lambda of this, right? I want to control this on L2. And I want to control it by something here, whatever the best thing is I can put there, of course, times the L2 norm of f. So the first part of that, d1, satisfies this bound. Okay, stating it rather generally for the moment, and we'll get to how we need to optimize this later, optimize our choices later. So I haven't chosen R yet. I'm just letting it be sufficiently large so that I can use the same R across this whole dyadic range. And when I do that, and I pick some arc from the Fourier dissection, some fraction a over q, I get this as my bound for the L2, the L2 boundedness of the maximal function of that first error term. Okay, it looks a bit gnarly, but it falls out naturally from the proof. So are there any questions at this stage before going into the proof about like what this means or what I'm even trying to do or anything like that? Is it clear that this is a thing I want to do? Okay, I'll take silence as a yes, or a resounding yes, that this is something we want to do. And yeah, let's go ahead and get to it then. Right, so I'm going to use this main L2 inequality, which converts. Okay, so main L2 inequality. Right, it converts the supremum over lambda between lambda and twice lambda into a supremum over C on the torus. Okay, that's roughly what it says. And what that means precisely for this setting is that what I need to bound actually is the following. I want to bound the integral of IAQ of the supremum over all C on the torus of this sum, the absolute value of the sum over M in ZD. Well, this is of course fixing A over Q. What do I have? 1 minus psi of Q C minus M times the Gauss sum. And the Fourier transform. This is the Euclidean Fourier transform. Oh no, not that yet, sorry. Yeah, it's the Euclidean Fourier transform of this HR of t x c minus n over q. And this is integrated with respect to t. Okay, since, yeah. So that's what that's a mouthful. That's what we want to do. All right. Now, first off, I of a over q, we know what the length of that is, basically. It's at most 1 over q times x. Okay, so really, all we need to do is understand what's a uniform bound over c for this and t. Then we just multiply by the length of the interval times whatever the supremum is right here. Okay, so that's what I'll do. All right. So the first piece into doing that is, of course, something that I've already recorded, getting a bound for the Fourier transform of this h function. So just as a reminder, we had that this was bounded by so this is c minus n over q. Fourier transform, absolute value, is at most some constant depending on n and the dimension. What did I say? I said r, the d minus n, 1 plus r squared t to the n, and then 1 plus c, c minus n over q to the minus n. Okay, that's a bound that's uniform in t and c minus n over q. Now, what do we have here? Well, we have that's the distance between this point, c and n over q, is bounded from below. Okay, in particular, we know that we have q c minus n is always, say, greater than or equal to 1 over 4, or maybe even a half or something like that, right? So that in particular, of course, that means also c minus n over q is greater than or equal to 1 over 4q. All right. And we can use that to sum up, to sum up this part right here, this bound up here over n. Okay, so we do that by looking at supremum over t and c of the sum over m and zd, 1 minus psi qc minus m times this Gauss sum, then times this Fourier transform. So I just apply the triangle inequality. So I move the absolute value inside. I control all of these terms. Oh, there's a missing parentheses there. I also, so because I have this condition, I can rewrite that as now a sum over m, such that q, let's write it as c minus m over q is at least 1 over 4q. No, I don't like that. I'll write it instead as qc minus m is greater than or equal to 1/2. So I don't have to worry about this anymore. And now I'm just looking at the absolute value. No, let's not do that. So I'm just looking at the absolute value of each of these terms in here. So this is equal to T, C, sum over M. And I have a uniform bound for the Gauss sums, right? And I have a bound for this for Euclidean Fourier transform. So let's plug that in, both of those in. This is at most up to some constants depending on dimension and depending on n. Well, the sum over m minus qc greater than or equal to half. What's the bound for the Gauss sum? That's just q to the minus d over 2. What's the bound for this Fourier transform? Well, I just said that. It is, and I've already forgotten. Okay, oh, right, r to the d minus n, 1 plus r squared t, and 1 plus c minus n over q to the minus n. So that bound comes out. Doesn't depend on anything right there. Yeah, actually, all of this does right here. So this is, of course, just q to the minus d over 2. It's a lot of fun to watch people crush through some inequalities, right? Right. And then, right, that's the soup over T and C times a sum. So I will just do something here. I will multiply by Q on this expression. All right. And then that means I have to take out Q as well. So that means I multiply by Q in here, and I should multiply by Q to the N. Yes. And I know that this thing right here is always at least a half. But it's actually getting further and further away as well, right? So that means I can get a bound on this as it goes to infinity. And in particular, this whole box, this whole sum right here is O of 1. The sum for something that depends on n and d. All I have to do is choose n here to be, say, twice the dimension. And I can make this just depend on n. All right. That means I'm left with this part as well. So let's rewrite this. That's at most something depending on the dimension, the soup over T and C of, I want to write this as R squared over Q, so D over 2, where I've combined this part, but not that factor of n. And then I've got the factor of R to the minus n and Q to the n. So that'll be an Q over R. And then I can plug in T here is at most 1 over Q times X. So that is, oh, the stray mark should have been at most this plus R squared over QX. Yeah. Right. Okay. So that's how we get the first bound. And, oh, sorry, all of this, of course, is to the n. And that matches with what I got, yeah. Okay. So I think I wrote something slightly wrong. This should have been R squared QX. right there. That will not that will not affect us later on. Okay. Were there any questions on that? I have a couple more pages for the proof, but questions? All right, I'll push on a little bit further before taking a break. I just want to introduce the major arcs and minor arcs and use Weil's inequality to get a bound for the minor arcs. Okay, so remember, I'm going to choose some auxiliary new parameter y. It'll be a lot smaller than x, but it'll also go to infinity as lambda goes to infinity. And our major arcs are going to then be all those, the intervals attached to all those fractions whose height is less than y, or at most y. And the minor arcs are going to be all the ones that have a big height, meaning at least y, but at most x. Okay. And we'll soon choose our parameters. X will be r to the 1 plus delta, so a little bit bigger. So the power will be a little bit bigger than 1 in terms of r, and y will be a little bit have a power that's a little bit smaller than 1 in terms of r. It's going to be r to the 1 minus delta. It's the same sort of choice we made when we did the circle method to count the number of representations for sums of squares. And so for our first major arc approximation, we can deduce the following. If I assume IQ is sufficiently small, meaning it's going to be on a major arc, and I assume that my Fourier level is sufficiently large, so those are consistent with the choices I said we're going to make at the end, then we can find that we have the following bound. Did I do that wrong? Yeah, so how do we get this? Before we had Q, oops, sorry. We had, scroll up a little bit more. Nope, don't have it. I just said that we can do the following. We get as our bounds r over, nope, q over r plus r squared over qx to the n. And then we have this is r squared over q to the d over 2. And how are we going to get this sort of bound? Well, the point is we're going to pick, we'll pick things so that each of these summands here is slightly, is a power of r, like r to the minus delta. So it's something that decays as r goes to infinity. And we choose n sufficiently large so that it's going to offset this factor of r to the d appearing over here. Oh, appearing right here. And that just leaves us with q to the minus d over 2. And then you sum up over all the a's and q's. And since it starts at 1 and d is, this is assuming, of course, d is greater than or equal to 5, we get that this sum is summable, and it's just O of 1. Okay. So I'll stop there for now, and we'll take a 10-minute break.